today I'm going to review a bit what we did yesterday, and then introduce, define what are correlation function and how we can compute them using the generating functional. And I think tomorrow we'll go to just an introduction to fermionic path integral, just for you to, if you're not already so much familiar with Grassmann numbers, this kind of thing, then it would be good to introduce before jumping in to QFT. But so before that, let's just maybe start with a kind of summary of what we are trying to do using yesterday the perturbation theory. So the idea was we were starting from the action of the anharmonic oscillator, and then the idea was to find the ground state energy, at least perturbatively. So we compute it at the first order, okay? So, and why I'm going to take the time to summarize everything is because the technique that we use here is quite general and really mimic what you're going to do in standard perturbative theory in QFT, okay? So I just want to give you, again, the main steps. So the idea, so this is from yesterday. So the idea was, the first step maybe, is that you need to be able to express the ground state energy as an expression involving a propagator, okay? So what, in our case yesterday, so how did we do that? What was the expression? So we use that the ground state energy can be expressed as so here the idea was to say that when we consider, so we were still working with Euclidean time, okay? We did a weak rotation. So then if you look at something like this object is of course going to be dominated by the ground state, okay? If you look at when then tau goes to infinity. So the idea here yesterday was to express this as a limit, okay? We introduce this beta related to the time. And we introduce a propagator that we computed a very simple one. Instead of taking any arbitrary initial point and final point, we decided that it was easier to just work with initial and final point are both 0, okay? So this was the first step. And so then what was the idea? The idea here is that, so this propagator is the propagator written in terms of the action of the system we are interested in, okay? And in our case, we were interested in, so this anharmonic oscillator, okay? So then the next step is really to be able, so inside here for the action, to separate the Lagrangian into something that we are going to call the free part, which is going to be the quadratic part, and an interacting part, okay? So this is free. So here it's going to be the quadratic. So it's not really completely free because in our case it's going to be still the harmonic oscillator. So here it's beyond quadratic. Okay, so in our case, indeed, we were working, what was the definition here of this propagator? we could write it, of course, as a path integral. With, so the action we consider here okay, so and sorry, so this is an action, so there is an integration. So where is my, so what I call here the free part, okay, is this part, even if it's the harmonic oscillator, okay, and this part is the interacting. Okay, so this was quite the important feature of the system we were considering, okay? And now, what was the more? So now we want to work in the path integral formalism, and so within this formalism, we really want to say that the interacting propagator can be written in terms of a free propagator with a source term added. And so what was this free propagator with the source term added here? I mean, it was exactly this free part, but instead of considering this interacting part, we add something which is going to be linear in x, okay? So it still can be still considered, the total thing can still be considered as free because we are going to be able to treat that as a quadratic or Gaussian propagator, okay? So here, we were considering this object with here my action is so just the same free part plus a source. And what was the relation between these two propagators here? So we want to write this propagator, or in fact, the only interesting part we're interested in is this interacting part, but let's, we can write the complete one. So what was here? How do we relate these two propagators?
Like exponential operator on
yeah, so the exponential of yeah, so okay, so we're going to apply. So here, this was equal to, so now where we consider functional derivative with respect to to the source. And apply to the free propagator with the source term, where then to obtain exactly the same result, then you need to put j equal to 0. Okay, so then what was really important in this computation is that, of course, you need to be able to compute this explicitly as a functional of J, okay? So it's the same thing that you tried to do in the tutorial yesterday, even if you have, instead of considering this propagator, but just if you work with an ordinary exponential, an ordinary integral with a Gaussian plus quartic term, then you can apply the same approach here by using a normal derivative then, okay? But the important point was that this term, or the exponential in terms of J in the case of the ordinary integral, has to be able to, you need to compute it explicitly, okay? So this is what you did in the, so the free, okay, so this is a really important feature of this free propagator. You want to be able to compute it explicitly. So this is more or less the part that you did in the tutorial, try to compute this object. And since it's only quadratic, okay, with just a linear term in J, you can really show that, because you know that this is going to be equal to exponential of okay, so this is a general feature for path integral, is that you know that the path integral can be written as a first factor and a second factor, which is going to be this phase, where here you have the action evaluated at the classical solution. Yeah?
Is the exponential of the functional derivative, is that integrated over tau?
Yeah, sorry. So here, okay, thanks. And so really, what you have to do is to solve a classical problem, okay? And what is this classical problem is to find the classical solution. And then evaluate and to find the classical solution, again, so we are dealing with the case of the harmonic oscillator with the source. So if now you look at the equation of motion, you're going to get some kind of non-homogeneous, inhomogeneous differential equation. Okay, so it's going to be the differential equation you have for the harmonic oscillator plus with a right-hand side term. Okay, and so the way to deal with that is, of course, to go to deal with Green function. Okay, so here it's what you did in the tutorial explicitly. It's to find explicitly what is the Green function solution of this differential equation, and then what is the classical solution in terms of this Green function. Okay, so then once we have this, we can compute this as usually we do a perturbative expansion here, okay? And we can compute any order, in fact. So yesterday we looked at the first order. In the tutorial, you also look at the first order. But you can see that if you expand that to more order, then you get more corrective term. So this is an interacting propagator. So written in terms of this free propagator with the source. To a perturbation expansion at any order. In lambda. So, okay, so it's a perturbation in lambda. This is a function of lambda. Okay, so you want, so the perturbation in lambda comes from the perturbation of this operator here. Okay, so really here the idea is to write that. You can expand this as any order. So the first order is the one we considered yesterday, where you will have to do let's write it like this. And then the second order will be something like this, where you consider this plus correction in lambda 3. Okay, so you can really go on, and then you apply that, of course, to your free propagator with the source that I did not. And then you evaluate when J is equal to 0. And so from this, of course, when you have this, you get directly the ground state, okay? Because you just now do this limit on this expression you get. So you get the ground state at the same order, okay? So then you get the ground state at the same order. Just using the limit here. Okay, so any...
Also integrated over tau.
Sorry?
He's also integrated over tau.
Yeah, so... Yeah, I guess I forgot that. So we have like... And then, of course, you need to add. Okay, thanks. Any question on this method? So we're going to see that, in fact, this kind of, even now we're going to talk about correlation function, what we call the function, and we can write this in terms of the functional derivative. In fact, the functional derivative is going to be exactly defined as here, meaning we're going to introduce a source, and then we're going to get act with a functional derivative. Okay, so now in the homework question for today, I ask you to yeah, I told you that usually in the literature you're going to see that E0 is obtained when you do the perturbation of you look at the perturbation for the what was the so-called partition function, and it's what I asked you to compare in the homework. So I just want to make sure that everyone know what is the partition function, so we can really get also E0 from and this is one of the simplest quantity that to represent as a path integral, okay, in the quantum is, and so what is the quantum partition function? So again, here we're dealing with imaginary time, and this is defined as a trace of this operator, okay, and the path integral here can be written directly from the representation of the matrix element of the time evolution. So this means that here you can really write that this is the trace of the time evolution operator And now if we introduce the position representation, what we get here is that we can write it like this. So I'm just introducing this delta function just to have two different x and x prime here. And of course, we know how to express this as a path integral, configuration path integral. So this, we know how to write it. And then we will be able to implement the delta function and the integration here. It's just going to tell you, so it's just going to implement. So the path integral here, if I just write it, is going to be, formally, is going to be something like this. Where here we don't have to forget which kind of path we are considering. Okay, so we're integrating over all paths such as the x prime, x of t prime is equal to x prime. So here I'm using, sorry, I'm using this notation. So f of 0 is this, and x of okay, so if now we implement the partition, the delta function, and we integrate, it's just going to imply that the contribution to the path integral are the path that satisfy some periodic boundary condition, okay? Because you want that x of 0 is equal to x of beta h. So then now we can implement the delta function, and we get a simple representation for as a path integral for the partition function as just where now the path that we consider are satisfying this boundary condition. Okay, so this means that either you consider closed path. Okay, so here it's going to imply that you consider any closed path or a periodic function. With here a period of okay, so this was just to relate, and of course you can show easily using this definition. So now if you go back to the initial definition and now you expand that in term, instead of representing that using the position basis, if you use now the eigenstate of H, okay, you really get very easily that this can be written as just the trace of, so without the trace, just the sum. And so from this expression, you really see that indeed using the same kind of analysis that we did before, okay, where you take the limit, you take the log divided by beta, and then the limit of beta goes to infinity, you get the ground state. Okay, so this was just to relate to the homework question and from maybe what you're going to see more in the literature using the partition function. And of course, since the only difference between this function and the other function are some constant, when you take the log and you divide by beta and take the limit, you won't see the difference. You really indeed get the same result. Okay? Okay, any question here? You can read my handwriting. So yeah, here usually I use this bracket to define the path integral. Okay, so the next thing I really want to introduce is the notion of correlation function and generating functional. So I'm going to give you the definition of this object in the context. I guess maybe you're already familiar with this in QFT. But I'm going to give you the equivalent in the analog in quantum mechanics, okay? So this kind of, the analog of correlation function from QFT would be this kind of object. And then so this is what we call either sometimes a green function or a correlation function. And a correlation function which depends on n different time here can also be, it's sometimes called the endpoint function, okay? So these are things that you should have seen maybe already in QFT. So now what we want to do is to find a path integral representation of this object, okay? But there are several things to clarify first. So first here, what is this operator? So here, I'm just going to say that it's a time order product or T product, okay? And it's acting on Heisenberg operators here, okay? So let's first maybe, so here what is important is that it's Heisenberg operator, and so we will have to translate a bit because to define the path integral formalism, we were in the Schrödinger picture, so we will have to translate a bit everything in the Heisenberg picture. But let's maybe first define this notion of T product. So this is defined for any Heisenberg operator, A, T, and B of T. Okay, so if I consider only two, and then you generalize to okay, I can use the Heaviside function to write it explicitly, and then so this is when T1 is greater than T2, so sorry, it's not plus T1 if T2 is greater than T1. And of course, you can generalize this easily to more than, so here is the Heaviside function. And yeah, so this can easily be generalized to the case of more than two operators. And of course, if you have n operator, then you're going to get n factorial terms here, okay? Okay, so now, how do we, so one of the issues here is that this is the Heisenberg operator, okay? So to start with, we need to really recast the path integral in terms of Heisenberg representation object, okay? And so first, maybe so first point is the relation between the usual Heisenberg operator defined in terms of Schrödinger operator. So you know that here you get x of t is just given by yeah. And so here, since we're dealing with this issue of defining Heisenberg, I'm going back to the real time, okay, just for a while. Or also, I'm going to take the opportunity to take, so this is the Heisenberg operator, okay? So this is the Heisenberg operator. So this is to use another method than to do directly the weak rotation. We're going to stay with time real, and then when we will have to take the limit. Oh yeah, maybe just one point before going here. So there was this remark in one of the homework that you didn't see really why the weak rotation was needed, because most of the calculation was possible in terms of the without the weak rotation. And you're right that at least the computation of the free of the propagator for the free particle, or the computation for the propagator for the harmonic oscillator could be done without doing the weak rotation. As I explained, you already did that a bit in one of the tutorials, is that then instead of dealing with Gaussian, you have to deal with complex integrals, okay? And then you do some contours integral, but you can really do all the calculation. Then to express this ground state here, we see that, or to define this partition function, the partition function is always defined for this imaginary time, okay? And here the limit is possible because we are with the imaginary time, meaning that when beta goes to 0, you get indeed that all the other terms are suppressing, and the dominant one is going to be E0. But so let's go back now to real time for here and just try to understand a bit what would be a path integral if we write it in terms of Heisenberg representation object, okay? So this is the question. Heisenberg. Okay, so first, the link between the Schrödinger one and the Heisenberg one. So this is just simple. So now let's look at the eigenstate, maybe of this Heisenberg operator. And in fact, usually if this is time dependent, you can label your eigenstate by, of course, x and t, where x is going to be the eigenvalue, given you the eigenvalue, and t tell you that you are at a given time t here, okay? So this shouldn't be confused with, it's just a parameterization, and it's not to be confused with the dynamical time of Heisenberg or Schrödinger, in the Schrödinger picture, where your state really depends dynamically on time, okay? So here, this just means that you have this, and it's at a kind of given time, okay? It's when you measure, it's an instantaneous eigenvector here. We can see that as eigenvector. And it's not, so the parameter t here is not dynamical. And so what is now the relation between the time independent vector? You have that here. And so if we want now to rewrite our path integral using this term, this vector, what do we get? So if we now look at the propagator, so here, what do we get? So if k is defined as between, let's say, then we know that we have this relation. Okay, so in terms of this new state, what do you get? So here, this means that this is going to define, and this one can be just seen as x. taken at the time 0, okay? So this is a new way to write like the path integral. So now this means that, and this we know how to write it as a path integral, so we have now this relation, okay? So now it's of t, and of course I'm considering now the action, which is not the Euclidean action, the usual action, and I have an I coming from the fact that I'm considering t. But I told you one of the first lecture was once you have your weak rotated propagator, or if you want the propagator return in terms of the Euclidean action, you just have to do the inverse of a weak rotation to get back to the classical action, okay? Okay, so this is what we're going to use now to define this object, okay? So first, I'm going to act with we're going to do that in 2 steps, okay? So the first step is going to look at the action of this time operator on any vector, okay? Not on the vacuum state, okay? And then look at the matrix element. So if you want, look at the matrix element of the T product of some Heisenberg operator between any state, and then we will try to see what does it mean to look at the vacuum, how to extract the vacuum from that, okay, the vacuum contribution. So first, any question here? Okay, so maybe, so I'll let you, well, you can ask question also later if the question comes later. So let's first consider now, so we want to consider the simplest correlation function. So we're just going to consider this one, which is also going to be called the 2-point function, okay? Okay, and so as I said, we're going to do in 2 steps. So the first step is going to look at this, just object, so meaning that we look at the time ordered product, the T product of xt1 and xt2 between 2 arbitrary vector, and then the next step will be to extract the ground state or the vacuum contribution. Okay, so let's first focus on step 1, and this would be step 2. And yeah, I should say that yeah, I haven't really found a nice way to present that to you, the second step. So hopefully, yeah, maybe with discussion, we will end up with something clear, but I'm not really happy with the way it is explained usually in the literature or anything. Oh, we will see. Okay, so let's first focus on this, and let's first suppose that T1 is, so it's the first step, and we're going to first suppose that T1 is greater than T2, okay? So this means that if I look at this, what do I get? So between x0, so T1 is greater than T2, so how can I rewrite this? It just means I can get rid of the T operator. So what do I get here? So if just looking at the definition, you just get that this is okay, and now let's introduce some identity resolution between these two. Okay, so what do I want to do? Yeah, okay, so I want to look at the matrix element of this object, okay? So I'm going to introduce the resolution, identity resolution between here and here. Okay, so here, and I'm choosing that this is at a given arbitrary time t1, at the time t1. x2, t2, and then I need to consider this object. Okay, so what does it mean here? What do I have? So here, this can just be rewritten as, so x1 and x2 are going to act on this vector, so I can get out x1, x2, which are not just number now, okay? And I'm left with this matrix element. T2. Okay, and so what are now these objects? Okay, we just said that this object can be rewritten as some path integral. Okay, so here you know how to rewrite these three terms in terms of a path integral. Okay, I remind you that the aim here is to write this object as a path integral. Okay, so we use this decomposition here, and so what does it mean? What do I have here? So here we want to find as path integral So I'm just using the previous result, and so what do I get here? x1, x2, and then I'm going to get, so this gives me the first path integral. Where here, what are the boundary conditions? Okay, the condition on my path is that you want that x of t is equal to x prime. So maybe it's too small. Is it too small or like? Yeah. From the beginning, you mean?
That's the last.
Okay, you're nice. Not telling me that from the beginning, and I'm not going to rewrite everything. Okay, so here I'm keeping. Okay, so I'm just going to replace that by this. I know how to write this as a path integral. I know to write it as a path integral. Path integral. Okay, so I keep that, and I just write these three terms as path integral right now. Okay, so let's do that. So here, so it's not much bigger, but hopefully you know what I'm talking about. So. Okay, so let's write. So what is important here is now this condition on the path for each of my path integral. Okay, so here the condition is that at x of, okay, let's try again, x of big T has to be equal to x prime. And the initial condition was that x at T1 is equal to x1. Okay, so this was the first product. Then I still need to add 2. And of course, it's a really bad strategy to have started. So this is times, and I go in here, okay? So then the second path integral is going to be, So this is something very similar here, where now it's going from x. So the path has to satisfy that at initial point time t2, it's equal to x2, and then x of at time t1 is going to be equal, final time t1 is equal to x1. And remember that here we are in the case where indeed t1 is greater than t2. Okay, so initial time is t2 for this interval, and then it's t1. And then times the last one, which is also just a path integral, where it's going to be formally written like this. And what we have to keep track of is this initial condition. So initially at time equals 0, x of 0 is just x. And at the intermediate time t2, it's equal as x2. Okay, so here, this is a product starting here, and I have three terms. The first term is here, the second, third is here. So sorry for writing that. That's kind of. So what does it mean here? So the first path integral starts from the initial position x, and then go to a kind of arbitrary position x2, okay? Then the second one starts from x2 at time t2 and go to x1. And then the third one go from x1 to the final position x prime, okay? And so here you have an integration over dx1, dx2. So this means that you integrate over the two arbitrary positions. And so the fact that we integrate over the two arbitrary positions here, this means that we can combine the three path integral together with the integration over x1 and x2 into just one path integral, okay? Because here we're really integrating over any possible. So this means that we're really going to have any possible path from. And so the combined path integral is going to be a path integral that has the path start initially at x, and the final point is x prime, okay? And you see that because here you integrate over all these possible x1 and x2, you really got that. So here, the result that we get is that if you look at this matrix element in this picture, from x0, this can be just written as a unique path integral where you only impose that x of the final point is x prime, and the path at the initial time is x. Then you have your path integral measure, and now x1 and x2 are just function of time. And this calculation has been done in the case t1 is greater than t2. Okay, so now we want to have this valid for any t1, t2. Yeah.
Sorry, but why isn't there a minus sign in the exponential I action? Because if we took a representation, like t becomes minus I tau.
Yeah.
It's just a detail, but since I'm not very comfortable with representations, I just want to make sure on this one.
So your question is if there is, so if it's is or minus is? Yeah, so maybe this is, Yeah, so I guess it's minus, what did I write?
It's minus.
Sorry?
Should be IS because you have the Euclidean action here.
Yeah.
It's integral over time. You replace it by minus IT. So
Yeah.
that minus goes away and you turn into plus I, right?
Yeah. It's t go to minus I tau, so
So tau is IT.
Yeah, so you have a t tau integral here.
yeah.
And then if you have a minus, that minus goes away and you have an I outside.
Yeah, so it's correct, it's fine, no? Right? Any, yeah, sorry, I'm, yeah, I think it's, but that's if we do the other way around. So sorry, I'm getting confused myself here.
So there you would get a
Yeah, I think, no,
minus from exponential, which should be right.
I would say that this is correct. Yeah. Yeah.
If tau is the real time, and then t is minus I tau, and it's the imaginary time, and we get to minus in the imaginary time, then to go back to the real time is just tau equals plus IT, so you just replace t by IT.
Yeah. And then you get,
There's still minus because there was minus initially. It's not important,
But
so
you have to give us a differential so that things have a change, right? It's minus 8, and if you have a minus, it's higher, so
no, it's, so. Oh, yeah, so I keep that in mind because just right now I cannot think really. That's right, but just to finish the argument here, because yeah, it's not affecting, okay. So if now we just, yeah, I know. I think I know the answer. Okay, so let's finish that. Okay, so we consider the case T1 greater than T2. If now we do the same thing with T2 greater than T1, what are we going to get as a final result?
Swap.
Okay, but this is just function of time. So is it like x1 of t times x2 of t? Is that the same of x2 of t times x1 of t? It's not operator anymore. So it's the same. So what do you get? Yeah, the same thing, okay? And in fact, it's just, so if the time ordering is done properly on this side, the conclusion is just that the path integral is doing the time ordering automatically, okay? Because you can see it from here. This is going to come from, so where the time ordering is important is from here to here, okay? When we go, so at this stage, okay, when we decompose, otherwise we should choose the identity resolution we would have exchanged, and then because, so what is important is that here we want to go from an initial point to a final point, okay? So time has to go from T1, T2 is less than T1, okay? So here it's indeed a path, the path is going from T2 to T1, and this comes from, so on the left-hand side, you have to be careful that the time ordering is correct, but then on the path integral is, you can say that it's taking, is doing that automatically, okay? So here it's going to be the same. And so what is nice is that, so what does it mean? Is that it's a kind of magical, the path integral ordering automatic. Okay, and really what is important is that indeed you have the time ordering done correctly in order to be able to decompose these three things into path integral, or you could, even if it's not, you could always do path integral, but then if you want to recombine them, it has to be in the ordering has to be taken into account here, okay? And then at the end, it's done automatically. Okay, nice. So you can really generalize this for any number of x now operator. So in the case n greater than 3, you just can obtain that can be written as a path integral with the right boundary condition. And then so now you have a product of just function. Sorry, it's x, yeah, evaluated at t1. Okay, so Elliot, the answer to your question, sorry, it's that here you also have, you remember it's a Euclidean action. Remember that the sign difference between the potential and the just the kinematical term is with a minus. And then because you also have, you remember that it's what you did in the tutorial yesterday, you did to compute the green function, at some point you had to take a derivative, okay? But it's with Euclidean, so here you have another sign, so it's compensate, you have another sign, okay? So here it's not only that you replace, it's also that S now is S Euclidean, and here it's S, okay? Yeah.
Is there a difference between x hat and x hat sub I?
So what is the difference between?
So like at the top you wrote the Green's function as just x hat evaluated at different times, but then we switched to
yeah.
Hat sub 1, x hat sub 2.
This is, yeah, so so yeah, there is no, so here there is only one, and your question is in the notation I use here, which is yeah, so here it just why did I choose this x1, x2? So no, sorry, there is no, and here it's just to simplify notation, but yeah, it shouldn't be twice the notation. Yeah, sorry about that. Yeah.
So what do x1 and x2 mean in that final integral?
No, so here, yeah, and x, it's x, it's a function x evaluated at 2 different times. Okay, okay, thanks. Yeah, sorry about that. And yeah, here I have it correctly. Avin, do you have a question?
Yeah, I'm not sure I understand how you do the integral over dx1 and dx2. Can you explain again?
Okay, so what is the definition of this quite formal expression of a path integral? Okay, it means that you integrate over all possible paths satisfying this condition. Okay, so here what we are just saying is that this expression can be decomposed into this integration over x1 and x2 times the product of 3 different path integral, okay? Where you can see that the first path integral is just the final point is x2, and then this one, it's from x2 to x1, and then from x1 to x prime, okay? And so for all these three pieces, this means that you're considering all possible paths. So for the first pieces, going from that just the path satisfies this condition, then this condition and this condition. But you see that since we're integrating over all x1, x2, meaning all these two arbitrary positions here, in fact, this product, instead of here, we were really, so we're starting from, so let's say that we have x in terms of t, and so from 0, and then we are interesting, so here t2, okay, and right now we were, instead of looking at all possible paths, starting from x0 to xt, okay, where we're considering all possible options, we were looking at intermediate time, okay? But here, at this intermediate time, it can take, the value can be, is arbitrary, okay? So, and it's the same here. So, in fact, instead of cutting this into 3 path integral, you can really see that as really saying that it's only one, combine that with the integration over x1, x2 as one path integral summing over all possible paths from the initial point to the final point. Okay?
Yeah, thank you.
And yeah, and just the important again of the ordering is that indeed, if it's ordered correctly, you can indeed combine them because you indeed go from one path integral to from a path going from an arbitrary x0 to an arbitrary point at t2, and then a path integral from this arbitrary point to another arbitrary point at time t1, and then this last, okay? But so you see that here to recombine the pieces, the ordering was important, okay? And so if we change the ordering here, then we're going to, of course, decompose that in terms of something like here from T1 to T2, okay? But then again, since at the end, we combine for all possible paths starting with initial and final condition, it's the final expression is the same, okay? So the final expression is the same, but here it's really, the ordering is really important. Okay. Now the question is, before going to try to so our initial motivation was to define this object, so what I call the correlation function, as a path integral, okay? And this correlation function are defined with the vacuum state, okay, or the ground state. And here, we are just dealing with arbitrary state right now. But even at this stage, the question is then, how do you compute this kind of object, okay? And this is going to be related to the approach we have used here, saying that indeed what we're going to do is, again, introduce something with a source term that we know how to compute, and by acting with derivative on this source term, we want to get some x going out, okay? So what is, here's the idea, and then, so we are still in the first step, just trying to compute this kind of object. So now we wrote that as a path integral, but now how to compute that, okay? So this is path integral, so this was the first aim, but now it's still nice to have this very formal expression. It's how to compute and so the trick we're going to use is very close to the one we use here. So let's see. So this means that we're going to consider our action, and we're going to add the source term, okay? So contrary to here, so here's the issue why we were not able to compute. The thing is that we were not able to compute it was due to the complexity inside the action. Okay, so here we're going to consider that we have an action, we know how to, so we're going to consider the case where now if I remove this function, I'm able to compute this path integral, okay? So of course you have seen that there are not so many cases I'm able to compute explicitly. It's when S is quadratic, meaning it's more or less the harmonic oscillator or the free particle right now, okay? So, but let's assume that we have some S, and if I don't have that, I know how to compute this, this path integral. And the idea is that I want now to relate this path integral to the path integral I know how to compute without this X, okay? And the way we're going to do that is, of course, if I know how to compute, so how to compute that, so the idea is kind of use the trick we use in perturbation theory. So we're going to consider this action with a source term. Where now, and so really the idea is that if I know how to consider, to compute the path integral for this action, with this action, adding this linear term in X is not going to be an issue, okay? Because you have seen that indeed when in the case, for example, if this action is a harmonic oscillator, then adding this term is still means that this action can be still seen as quadratic, and I know how to compute it explicitly, okay? So, well, usually I'm going just to use this shorthand notation. So now the idea is really that I know, if I know how to compute this object, which is the, I'm going to use this notation, so just the transition amplitude in the presence of a source, x prime t. So now in terms of this new state, instead of to remember that I'm using S, the action with the source, I'm going to put this subscript here. And so this is by definition what I call, again, I'm forgetting about H bar from the beginning. And now if I look at the functional derivative of this equation with respect to G, the J at a given time t, where t has to be between 0 and big T here, then I'm going to get, so now I'm going to do, as we did, the functional derivative of this equation, so with respect, and here the time we choose, okay, is going to be important. Well, now t is going to be between, of course, then what do you get is quite similar to what we, the idea we had yesterday is that here is going to get, so from acting with that, you see that now I have the I, so if I'm doing, and then I'm going to evaluate this at G equals 0. Okay, so then of course higher derivatives are going to be easy to obtain. You're going to get each time the factor I xt that is going to appear in the path integral. So this is nothing, but if you then evaluate, put j equal to 0, is going to be the matrix element of the time ordered operator x in the presence with, so here it's with, if I don't put j to 0, it's just going to be in presence of a source. And then if we put j to 0 at the end of the calculation, we're going to obtain this kind of relation. So that this object can be obtained from x to 0 So I multiply by minus 1 time n, and then I take multiple functional derivative at different time. Of rewrite this maybe correctly. So it's a functional and acting on the path integral of this with this action, but then you put j is equal to 0. Okay. So you want to. Okay, so you see that it's very similar to what we did in the perturbative theory. It's not for the same reason. In the perturbative theory, the reason was, okay, we have an action. We don't know how to compute that, but the term in this action can be obtained if I perform many functional derivative on a quite similar action, but with a source term. And now the idea is that, okay, hopefully I start with an action. I know how to compute the associated propagator to it. But then if I perform some functional derivative with respect to this source at given time, then I'm going to obtain this object. Okay, so again, the idea is if I know how to compute this object as a function of j, then this is much easier to do than to try to compute this explicitly. Okay? Okay, any questions now? Okay, so I don't think I will have time to finish what I was planning. So, so here we are the first step. Okay, to define correlation function. Now we still have to look at the transition amplitude between ground state. So because we want to obtain the vacuum to vacuum matrix element. Okay, this is the idea. So we want, instead of having this given state, we want from vacuum to vacuum. This is really the kind of object you're going to consider in 2FT. So and really the idea is that again, to get the ground state, it's a bit what we did yesterday, okay? So you either
Maite?
Yeah.
Sorry, isn't it just I to the n there?
you want to, so here it's going out a I.
Yeah. So each time it's just an I, not a minus I.
Yeah, but then you multiply, so you multiply by minus time, so you get, each time you get out a I, and each time you multiply your result by minus I. So minus I times I is 1. You want to get rid of that.
Ah, you want to get rid of that. Okay.
Yeah.
Sure.
Okay, because what you want to get, you see here I don't have any I. Yeah. So my minus I is just to compensate the I going out. Okay, great. Any other question? Okay, no. So really the idea is very similar to what we have seen yesterday is again that to get what we did to get the ground state energy, okay? So the idea was, if now I have a imaginary time and I take the limit t goes to infinity, okay? Then what is going to dominate is really going to be just the ground state, okay? And maybe we can see that just doing this small exercise. So if we just write this object, so now it's the second step. How do we get to vacuum matrix A? So really, let's look maybe as this object first. So just the propagator. That anyway, it's what we're going to be interested with. Okay, it can be with a source or without a source. We don't care about, right now we don't really care about the action. It's just that this can be written. Yeah, so for convenience, I'm just now shifting the initial time instead of considering from 0, I'm considering from -t because it's easier if you have something more symmetrical, okay? So let's just look at this. So here you can really write, if we go back to what we said, this can be, it's just -2, and then. And again, now I can introduce the eigenvector of my energy. Okay, and so here I just get the sum over n of and in fact I can of course factorize by this t, and then what I get here is the term 0. Plus the sum when n is different from 0 of En minus E0 and then okay, and so you see now that if we redo a weak rotation.
Is this E0 instead of En, the first one we took out?
Sorry?
The one we took out. No.
Oh, yeah. You're right. Thanks. It's the ground state, yeah. And so if you see that, if now we perform again a weak rotation, meaning t goes to minus tau, then minus e tau, then you see that here, again, we're going to get a -1 going out. And when tau goes to infinity, you get that this term goes to 0 very quickly, okay? So the dominant term is going to be this one. But, and so this is the idea that, and indeed what you get is going to be the same thing as if you were looking at this object, but evaluated on the ground state, okay? Because if now you evaluate this with the ground state, you're going up to some proportional factor. But again, since it's only proportional factor, and you remember that when we define partition function, anyway, we always normalize by something we know. We can always normalize by something that makes this proportional factor disappear. So here, really, the idea is that this can be seen more or less as something proportional to when so up to this weak rotation, but there is also another way to, instead of not doing a weak rotation, I'm going to introduce another way of dealing with that, is that now I'm going to consider that my t as a small negative imaginary part, okay? So I'm going to write it like this, which can be seen as where this is real, meaning that this is okay, and so we're going to see that instead of doing the weak rotation, we can work with this kind of t where we consider a small imaginary part. And then, of course, what is going to be the next question? The next question is going to be able to compute this object that we wrote for J, evaluated between the ground state. Okay, so here, just maybe let me finish. So here, this can be seen more or less as something proportional to where here it's the ground state. Okay, so this is just to give you a bit of an idea. And so now we're going to use that, in fact, to define what we call the functional generatrice. which is going to help us to define all these objects that now for from vacuum to vacuum, okay? And so let me write it explicitly what I mean here. So let's define okay, so the idea is that now we want to look at object like this, okay, correlation function. And we're going to use directly this formula. Okay, so this means that and in this case, where now we're dealing with the ground state and not in this object here that will have to be defined a bit better, okay? But the idea is really that, in fact, you take the path integral, but then now you consider this limit up to some normalization term. So here, you can write this. Well, this is what you call the okay, and so maybe just to clarify, I think just what was here so here, this can be really seen as yeah, so here, this is this, sorry. So this is this object, okay? So what I have, this path integral is this object. And if you want, really what I call the functional generatrix is the same object but instead of these two states, now I have the ground state, okay, with the normalization. So if you want, formally, you can write really that is, we're here now with the ground state, and I need to specify that indeed it's when J with J and normalized by the case where J is equal to 0. Okay, just meaning that here you choose the normalization J equal to 0. This gives you 1. So more precisely, what is this object? It can be, so it's going to be a kind of limit when you consider now let's go here. Okay, so we have seen that this limit can be obtained, this ground state is going to be obtained starting from that when you take the limit, okay? So here, if we go backward, we're going to get that this is, so Z of G. Keeping in mind that here I'm defining my T like this, okay? And yeah, well, it can be for any, in fact, minus T, let's say, when it's evaluated with the matrix J, and to get rid of this proportionality factor, I'm just dividing by the same thing, but when now J is equal to 0. And of course, you can write this as just path integral. So in terms of a path integral, you're interested in the case where now your limit is going to be when, so this is hidden in the kind of path you're considering. So it's going to be written in terms of the path integral. As the exponential of this S plus this source term added. Okay, where now the integration is going to be from infinity minus infinity divided by normalized by the same thing. Okay, so this is the definition, and the next step is, of course, to compute this object. Okay, and to compute this object, or at least the numerator, okay, this is really very similar to what you did yesterday in the tutorial, okay, because what you need to do, so of course you need to specify, to compute that explicitly, we need to choose specifically one S, okay? So since the only one we know to compute is the harmonic oscillator, let's take this one, okay? We don't have so many choices here. So here, let's assume that this is the harmonic oscillator, okay? Then you add again this source term. So it's really exactly what you should recognize this object, okay? If S is the action of the harmonic oscillator, okay? What I call S, then the path integral for S is more or less exactly, so of course I guess I erased everything. No, it's not here. Okay. But I think it was what I denoted K0J, except that now we haven't done a weak rotation, okay? So so it's going to be exactly the same thing, okay? You're going to look, so what are going to be the steps here, okay? To compute this object. You're going to, so we assume that this is the harmonic oscillator, so you know that this is going to be of the form a constant with respect to J, okay? And then an exponential or evaluated at the classical path. And again, what you're going to look at the equation of motion. So here you're going to get the equation of motion for the harmonic oscillator equal to, not equal to 0, but equal to J now, okay? And again, you're going to find a solution using the green function approach. Now you just have to be careful because here you have an I, meaning that you're going to get now your poles not on the imaginary axis like you did yesterday, but you're going to get them on the real axis, okay? So you just, but the fact that here we're using this time in imaginary time, or the time with a small imaginary part, which is negative, then you will see that you have only one good prescription to get your solution. And so you're going to get something very similar to what you get yesterday. And so the result is just going to be, so maybe I give you the result and then we can more have a discussion. So at the end, you're going to get that. So here, so the idea is to compute xc, and then you want to simplify by doing an integration. So maybe I can do this part. When you found the solution, so the solution is going to be written in terms of the solution of the harmonic oscillator plus something in terms of this green function. Okay, so all the work is to get the green function. But if you assume that we have the green function, then what we want to do is to evaluate. And so for this, the trick is doing the integration by part. Okay, meaning that you consider which is equal to but now it's the classical solution. So this is what you did yesterday, and several of you had a question during the tutorial, so let me just maybe so here what you do, you want to evaluate this one now that you know x of c, okay? But you can really simplify this by doing an integration by part, okay? So if you do an integration by part, you're going to get a term like x dot that you need to evaluate at the boundary part, okay? But you see that this term anyway, so in the tutorial yesterday, it was vanishing because we chose the boundary to be 0, 0, okay? But here, even if it's not vanishing, right now it's going just to enter into the constant. So for the moment, we don't care about the boundary. I just want to show you the trick that was used to find the solution. So then you get this integration. So I done the integration by part on the first term. So here, what do I get? I'm going to get minus x derivative second times x. Okay, so I can factorize, since I have some x everywhere, I can just factorize by xc. And this is going to be minus 1/2 plus minus 1/2 of m x, omega squared xc squared plus g. Okay, so then here what you want to do is that it's not for any x, okay, it's for the classical solution. So you want to use your equation of motion, but if you compute the equation of motion here, you see that you're going to do the derivative with respect to x dot and to x, so the two are going to vanish, okay? Whereas here it's not vanishing. So here it's really just 1/2 of a part of the equation of motion. So this from the equation of motion, you get that this is minus x. So this part is just minus g, okay? So divided by 2, sorry. So this is from the equation of motion. Okay, so what do you get here is just that this is equal to the evaluation of your action in terms of, in the classical solution, is simply equal to dt x 1/2. You have the 1/2 coming from here, c of t, g of t. And so I just give you what is. So from that, you get very easily, if now you know that your solution x of t can be written as an integral over t from of your green function times your source term, okay? You just get the expression for the generating function, which is very similar to the object you were dealing with yesterday, which is just going to be, with all the normalization taking into account, the exponential of 1/2. So you see the 1/2 come from here when you simplify your action using the equation of motion, because you're evaluating this action as the classical action. Then Okay, and here's the green function. I let you. It's very similar to what you did yesterday. And of course, the green function is going to be dependent on the system you're considering. Okay, so this is the result, and you see that what we want to do. So can I just talk again 2 minutes, or you really want to? You really want to go? Okay, I just concluding because tomorrow I wanted to talk about fermionic things. So then what is the idea of this is to compute your correlation function. You just take some derivative of that, okay? And of course, you see that now, contrary to what we did yesterday, the derivatives are at different points, okay? And so this means that here what you're going to get is having some high-order derivative things to take from this object. And then it's very helpful at this stage to then consider the weak theorem. And I'm just going to give you. So here, then the next step is going to take order derivative. Okay, and so it is at this stage that it's useful to consider, to consider this weak theorem, which is going to transform. It's a method for reducing this problem of doing some derivative to just a combinatorics problem, okay? So where you're going to transform this problem to and yeah, so I'm going to add this in the lecture note. I don't think it's free. I'm going to write it just for discrete time, but really the idea of this weak theorem is going to tell you that you can really consider this when you take all these derivatives and then you evaluate g to 0 are combining some component of this green function here, okay? And all the way you combine this component to these different components together is then the way you get the Feynman diagrams is just doing kind of a diagrammatic way of expressing this weak theorem, okay? So I'm just going to add that in the lecture note, and maybe in the tutorial or in the homework I will add a question just for you to think about it, but I guess you're already really tired, so